But okay, so this is the differential equation. How do we solve this differential equation? There's something kind of special about this equation. So this is, let's write out what's special about it. It is second order. It is linear. And it is something called non-homogeneous. Okay? If you've taken calc, maybe you suddenly become scared. Non-homogeneous. So these are a little tougher to solve. What you have to do is basically make a substitution to solve it. So let's do that. And again, like this is kind of the most complex math part of the course, and it'll get easier from here. But it's really not too bad once you understand it. So let's make this substitution. So I've copied the equation over there on the left. It's a little too small. But that's our solution, our differential equation that we need to find a solution for. So when you want to solve a non-homogeneous linear ODE, you can make this substitution. And you say, I'm going to assume that there's a solution, t of x. That solution, this is the thing I'm trying to find, can be broken into two parts. The first part is called a particular solution. And then the second part is called the homogeneous solution. Okay? The particular solution, we'll do that one first. That is just by inspection almost saying, can I find an equation that satisfies this ODE? Right? Can I, let's zoom in here. Could I guess some function t that if I take the second derivative of that function and then I subtract from it perimeter h bar over KAC times that function, is it equal to the right-hand side? So by inspection, we can find functions that match that. The problem is you can do that, but it's not the entire story, right? There's additional parts of the solution that you have to find, and that is that you find the additional parts by removing all the non-homogeneous stuff. So this over here, anything on the right-hand side, is the non-homogeneous part. Right? Any constants or anything that's only a function of the independent variable, in this case x. All of that is the non-homogeneous part. So we basically say the left-hand side of our standard form equation is equal to 0 and find the solution for that problem. We add those two back together and that's your full solution. Right? So it's really important that you do both parts, otherwise you don't get the full picture, the full solution. So let's first start with this particular solution. The particular solution we just, like I said, have to do by inspection, basically. There's a method for this that helps you do it a little bit more systematically. So let's say there's methods. Method 1 is inspection. Method 2 is called the method of undetermined and coefficients, or sometimes we call this MUC for short. So there's a particular method that goes with that. So let's maybe just walk through what the steps are here. Let's save room. So 1, write ODE in standard form. Step 2 is guess the form of TP to be unknown constants. Unknown constants multiplying the form, right? The form, I'll tell you what I mean by this stuff. The form of the right-hand side and its derivatives. Okay, that was a mouthful. I probably should have just wrote that out for you. But so write the ODE in standard form. That's what we've got there. Guess the form of TP to be some unknown constants multiplying the form of the right-hand side and its derivatives. So in this case, the form of the right-hand side is what? It's a bunch of constants, right? Everything there is constant. So the form of the right-hand side is constants. So what is a derivative of a constant with respect to x? 0. So we're going to guess that the solution looks like a constant plus its derivative, 0, which is just a constant. So I'm going to say this. So I'm going to guess Tp is equal to some constant. Now, I already have, I know I'm going to have two boundary condition constants. So let's save ourselves some trouble and just call this C3. All right, so I'm going to guess that the solution is Tp is equal to C3. Now my job is to determine what C3 is. So how do we do that? Well, I'm guessing the solution is this, so I'm going to plug that into the ODE and do the operations that are said there. So what I mean is, let's plug this in. So d squared Tp, which is d squared C3, dx squared minus perimeter h bar over k AC times t, which is now C3, is equal to minus perimeter h bar over k AC times t infinity. Right, everybody see what all I did was I just substituted C3 in where t was. Right, I'm saying that's the part I'm looking for. So the second derivative of a constant, if the first derivative is 0, the second derivative is also 0. So this term goes away. And now I'm left with two constant groups that are the same on both sides of the equation. All right, so this goes away, this goes away, and I'm left with C3 is equal to t infinity. So my particular solution for this problem, that is by inspection, or this sort of method of undetermined coefficients, I've determined that that particular solution is t infinity. So that's saying my function could be t infinity, it satisfies the ODE. But that's not the whole story, right? It's uninteresting if we just say that the temperature profile is constant through the entire fin. Like that doesn't help us. It's not the real solution. So now we need to go back and do the homogeneous part. So what I'm going to do is, I think I have enough time to get through the homogeneous part. I want to give you more, like this was a trivial example on the method of undetermined coefficients. So I think next time we'll come back and we'll do a little bit more detailed example there so you can see different cases. So we'll skip this next slide and then go to the following one that's numbered 4. So let's just do the homogeneous part. All right, so here we're going to be doing, finding the homogeneous solution. So remember what I said, we're trying to find a solution to this homogeneous part. So d squared t dx squared minus perimeter h bar over k AC times t is equal to 0. And I'm saying specifically here that we're looking for a solution for t sub h. Okay, I'm looking for the homogeneous part of the temperature solution. Okay, so this is actually kind of a short story here. If you want to solve this equation, you can go look at a table. I mean, you could maybe remember from calculus that there are like exponential equations or cosines or sines that you can use for this. And so you just want to go look at a table and do it that way. So if we looked at a table, you might recognize that there's a certain form, like the one on top there, right? D squared t dx squared minus m squared th. That's basically the form that we're solving, except that this m squared thing is the constant. So we would say, my solution looks like the one on the right. You could choose either exponentials or the hyperbolic version, which is quotient sinh. It's equivalent, right? You could choose either, and then you just say m squared is actually the stuff multiplying my original equation. So we can go back and do that. So I'm going to say, let's let m squared equal perimeter h bar over k AC. And then my solution is just t sub h is equal to c1 exponential of mx plus c2 C2 exponential of minus mx. Again, m is the square root of that thing above. Great, okay, so now we have our homogeneous solution, and we have our particular solution. And you just add them together, right? So my full solution, T of x, is equal to T h plus TP, which is this. I'm just going to copy it because I'm lazy. So copy this here, plus my particular solution. What was the particular solution? It was T infinity. So this is the general solution in temperature. Important things are you end up this process with two unknown constants. If you go through method of undetermined coefficients and you still have constants left over, C3, C whatever, you can't solve it. So that's a problem. You made a mistake. You should have two constants because you're going to solve these with boundary conditions. Okay? So leave it there. Stick around for office hours if you have questions.